Beneath your feet, at a depth of just 6 feet, the ground holds a secret that the modern energy industry has spent decades making sure you never think about. The soil temperature at that depth stays locked within a few degrees of your region's annual average temperature year-round. It doesn't care what the thermometer says in July. It doesn't care about heat domes, grid failures, or your electricity bill. It just sits there, stable, constant, and completely free. And for thousands of years, civilizations used that fact to cool their homes without a single moving part, a single compressor, or a single watt of electricity. The technology is called an earth tube. Research published in Energy and Buildings by engineers Lee and Strand using the U.S. Department of Energy's own Energy Plus simulation tool across 4 American climate zones found that a properly designed system can reduce a building's total cooling load by between 30 and 60%. It delivers air pre-cooled by the Earth itself before it ever touches your living space. So if this system is that effective, why isn't it in every new home being built in America today? And more importantly, can you still get one? Let's find out. Historical legitimacy. To understand why this technology was buried literally and figuratively, you have to go back to where it started. The oldest confirmed use of earth-cooled air systems dates to ancient Persia, in the same desert cities that gave us the Badger wind catcher. Persian architects understood something that took modern building science centuries to rediscover. The Earth itself is a thermal battery. It absorbs heat slowly, releases it slowly, and at subaquient depth reaches an equilibrium temperature that mirrors the annual average air temperature of that region, not the summer peak, not the winter low, the average. In cities like Yazd, builders combined underground qanat channels, irrigation tunnels that ran for miles beneath the desert floor with above-ground living spaces. Air moving through those tunnels was stripped of its heat before it entered the home. The result was a passive air conditioning system that required no energy input and no maintenance beyond keeping the channel clear. By the Roman period, similar principles appeared in the construction of wine cellars and granaries across the Mediterranean. The Romans understood that burying a structure just a few meters underground stabilized its internal temperature dramatically, not as a comfort feature, but as a food preservation strategy. In colonial America, the root cellar operated on the same physics. Farmhouses were built with underground rooms that stayed cool through summer and frost-free through winter entirely passively. These weren't primitive solutions, they were elegant ones. The problem wasn't that the technology stopped working. It's that the industry decided it was easier to sell you a machine. The science here is what is actually happening beneath the surface, and why the physics of this system is so compelling. The ground behaves like a massive thermal flywheel. According to the U.S. Department of Energy's Building America Solutions Center, deep soil in the continental United States maintains a temperature close to the annual average air temperature for that location, varying only slightly across the 4 seasons. In the Deep South, that number sits closer to 65 to 68 degrees Fahrenheit. In the northern states, closer to 48 to 52 degrees. But in every case, it is dramatically lower than the 90 to 110 degree air sitting above it on a July afternoon. An earth tube, also called an earth air heat exchanger, or EHE, exploits that difference directly. The system works like this. A pipe, typically 4 to 8 inches in diameter, is buried at a depth of between 4 and 8 feet and run horizontally for a distance of between 50 and 150 feet before entering the building at foundation level. Hot outdoor air is drawn into the inlet at one end. As that air travels through the pipe, it is in constant thermal contact with the surrounding soil. The soil absorbs the heat from the air. By the time the air exits into the living space, it has been passively cooled by the temperature of the earth itself. There are no refrigerants, no compressors, no motors, no moving parts of any kind. The driving force that pulls air through the system can be entirely passive, powered by the stack effect of the building, a solar chimney mounted at the exhaust point, or a combination of both. When paired with a solar chimney, the system becomes a closed thermal loop. The chimney creates negative pressure at the top of the building. That suction pulls air through the earth tube at the base. The air enters pre-cooled. The sun powers the entire process. The foundational research on this was published by Michalakakos, Santamoris, and Asimakopoulos in 1994 in the journal Energy Conversion and Management. Using a validated transient numerical model driven by multi-year real climate data, they analyzed the cooling potential of horizontal buried pipes across a range of pipe lengths, depths, and diameters. Their conclusion? The system's performance scales directly with pipe length and burial depth, and on peak summer days, the temperature differential between incoming air and the surrounding soil drives the system at its hardest exactly when you need it most. And crucially, that self-reinforcing behavior is what separates it from mechanical cooling. On the days your air conditioner is running at maximum load and driving your electricity bill to its monthly peak, an earth tube is at its most effective. The data drop, the performance data on earth tubes, is not anecdotal. It has been validated in peer-reviewed research across multiple climate types, including American ones. The most significant American study comes from Lee and Strand, published in Energy and Buildings in 2008. Using the DOE's Energy Plus simulation platform, the same modeling tool used to certify building energy codes, they tested earth tube performance across 4 di-errant U.S. climate locations. Their finding, now widely cited in the passive building literature, a properly designed earth tube system can save more than 50% of the total cooling capacity requirement in climates where the temperature differential is favorable. The research confirmed that pipe depth and pipe length are the 2 dominant variables determining performance, and that both are entirely within the builder's control. A broader review published in Renewable and Sustainable Energy Reviews synthesized decades of international EA research and found that cooling demand reductions of between 30 and 60% are the consistent, reproducible range across studies, climates, and design configurations. That range held across hot arid climates, Mediterranean climates, and humid subtropical zones. On indoor air quality, the comparison with standard mechanical systems is stark. The EPA estimates that indoor air is often 2 to 5 times more polluted than outdoor air. In a modern, airtight home with a standard HVAC system, air is mostly recirculated, providing very little fresh air exchange. An earth tube system, by contrast, delivers a continuous supply of 100% fresh outside air, preconditioned by the soil, with no recirculation of stale indoor air. And because the device consumes 0 electricity, every dollar of reduced cooling load is a pure gain, with no operating cost on the other side of the ledger. The villain act. So, why isn't this in every new home in America? The answer has nothing to do with the technology, and everything to do with who profits from the alternative. The modern American home building industry is built on speed and standardization. A production builder constructing 200 homes in a subdivision is not designing each structure around the thermal properties of the local geology. They are ordering the same HVAC package from the same contractor, installing it in the same 2-hour window, and moving on. Earth tubes require site-specific design, excavation, and integration into the building's passive system from the ground up. That is not a plug-and-play solution. And anything that isn't plug-and-play gets dropped. Then there is the regulatory trap. The International Residential Code, which governs residential construction across most of the United States, is written entirely around ASHRAE 62.2 mechanical ventilation standards. Because earth tube performance varies based on soil temperature, pipe length, and local climate variables that die by site, the system cannot be assigned a fixed, certified performance rating. It doesn't have an Energy Star label. It doesn't have a SEER rating. A building inspector who has never seen one will almost always require a mechanical backup system to be installed anyway, effectively doubling the cost of the build and eliminating most of the economic argument for the passive system. And then there is the most obvious reason of all. An earth tube, once installed, costs nothing to run and almost nothing to maintain. There is no filter subscription, no annual service contract, no refrigerant recharge, no replacement compressor at year 12. For the utility companies billing you every month and the HVAC manufacturers selling you a new unit every 15 years, a technology that permanently removes you from that cycle is not a product. It is a threat, honest limitations here is where most channels promoting passive systems lose credibility. They don't tell you what won't work. Earth tubes are not a universal solution. The DOE's Building America Solution Center notes directly that even an ideal system can only deliver air as cool as the Earth temperature at the depth it's buried, and during summer, that ground temperature at typical installation depths will run somewhat higher than the annual average shown on regional maps. In climates where the ground temperature sits above 65 degrees Fahrenheit at shallow depth parts of South Florida, coastal Louisiana, and extreme South Texas, the temperature differential may not be large enough to deliver meaningful cooling on the hottest days. The system still reduces humidity and preconditions incoming air, but it won't fully replace mechanical cooling in those zones. Moisture is the other critical variable. If warm, humid air enters the pipe and cools rapidly, condensation can form inside the duct. This is not a deal breaker, but it requires proper design: a slight downward slope in the pipe to drain condensate, a particulate filter at the inlet, and an appropriate pipe material, smooth bore PVC or high-density polyethylene, to minimize biological accumulation. Finally, soil thermal saturation is a real EACT. As the research literature notes, sustained use over days and weeks gradually warms the soil immediately surrounding the pipe, which narrows the temperature differential and reduces performance. This is manageable through intermittent operation, running the system during the hottest parts of the day and allowing the Earth to recover overnight, but it is a constraint that a purely mechanical system does not have, and an Earth tube is not a retrofit you can implement in an afternoon. Proper installation requires excavation. That cost is real and needs to be factored into your payback calculation honestly. Practical implementation here is what an earth tube installation actually looks like in practice, and what it will cost you. For a standard 1,500 square foot home in a hot climate, the recommended configuration is a single run of 6-inch smooth bore teep pipe, 100 feet in length, buried at a depth of 6 feet. The inlet should be positioned on the shaded, north-facing side of the property, elevated slightly above grade with a fine mesh insect screen and a coarse particulate filter. The pipe should slope very slightly around 1% grade toward a low point where a condensate drain can be installed before the pipe rises into the building. At the building entry point, a bypass damper lets you switch between earth tube cooled air in summer and direct outside air in winter, preventing the system from drawing cool ground temperature air into the home when you want warmth. The pipe itself costs between $1.50 and $2.50 per linear foot for 6-inch HT, putting materials for a 100-foot run at roughly $150 to $250. Excavation with a rented walk-behind trencher adds between $200 and $400 for a half-day rental. Fittings, inlet cap, filter housing, and damper bring the total to between $500 and $900 for a careful DIY installation. Professional installation, including design, excavation, and integration with an existing ventilation system, typically runs between $2,500 and $5,000 depending on pipe length and site complexity. Even at the high end, that is less than half the cost of a new central air conditioning system for a solution with no electricity draw and no moving parts to replace. For new construction, the optimal approach is to design the earth tube as part of the building's passive system from day one, pairing it with a solar chimney at the exhaust point, positioning intake and exhaust to maximize the pressure differential, and running the pipe beneath the building's thermal mass. This is the configuration Lee and Strand's research identified as delivering the highest performance: a self-reinforcing loop where the chimney provides the suction and the earth provides the cooling, entirely without mechanical input. The payoff: the earth tube is not a fringe idea or a back-to-the-land fantasy. It is applied thermodynamics. It is the same physics that kept Roman wine cellars at a stable temperature 2,000 years ago, validated by DOE-funded research published in peer-reviewed engineering journals, using the same simulation tools that govern American building codes. The industry didn't sideline this technology because it doesn't work. It sidelined it because it works without them. A system that never breaks, never bills you, and never needs a service call is not a product. It is a permanent piece of infrastructure like a well or a root cellar that returns value to its owner for decades without sending a single dollar back to the grid. In a world of rising energy costs and increasing grid instability, that kind of independence is not primitive. It is exactly what modern housing should have been built around from the beginning. If recovering that lost engineering and building a home that works with physics instead of against it matters to you, then subscribing and sharing is the simplest way to make sure this kind of knowledge keeps being found.